So the last topic about water I want to cover is that of water ice currently on Mars. Clearly, Mars is a cold desert planet currently, and so if and where we find water on Mars, it is likely to be in the form of ice. And I'll breeze through some of this stuff. I will basically want to focus on just a couple of aspects here. Clearly we've known for a long time that there are polar caps on Mars ever since early days of telescopic observations. What kinds of materials do we find in the polar caps on Mars? What kinds of material do we find in the polar caps on Earth?
Water ice.
Water ice. Okay. So what could we potentially find in the polar caps on Mars?
Water ice.
Water ice and carbon dioxide ice. Okay. So there was a question for a while. When the polar caps were first discovered by Cassini and Huygens and those folks back in the early days of the telescopes, they just assumed it was water ice because of making an analogy to what's known here on Earth, where our polar caps are water ice. But when we got a little bit more sophisticated, there was a question for a long time. Is it really water ice? Or we know most of the atmosphere of Mars is carbon dioxide. So is it carbon dioxide ice? Is it something else? It's basically both water ice and carbon dioxide ice. The carbon dioxide ice is more labile and will boil off. It will sublimate during the summer when temperatures warm up, and then freeze back onto the poles during the southern winter or the northern winter. But both of the poles have at least some residual ice cap of water ice that's there year-round. Water ice is much more stable than carbon dioxide ice, and the summer temperatures are never really going to get warm enough in either hemisphere, northern or southern hemisphere, during the summers there to melt off all of the water ice that's in the poles. Colin?
Well, thank you.
There are some differences in terms of proportion of water ice to carbon dioxide ice in the two poles, based on, we know the southern summer is short and hot, and the southern winter is long and cold, and the northern seasons are different. We have a cooler, longer summer. I think it's going that way. And warmer, shorter winter. So there are some differences, but don't worry about it. Just the main take-home message is that there's both water and carbon dioxide ice. The carbon dioxide ice is more labile, moves around more, and the water ice is more permanent. I want to focus a little bit, though, on results from the Mars Odyssey mission. One of the principal findings out from this mission really does deal with the distribution of ice around Mars. And so I want to go into a little bit of detail of how they determined that from orbit, what instrument was involved and how it works. So you get a little bit of the flavor of how these questions are asked, not just me telling you, oh yeah, there's subsurface ice around Mars. So Mars Odyssey was one of the earlier spacecraft from this second round of Mars exploration. It was pretty much the next launch window after the Mars Global Surveyor and Mars Pathfinder missions that were, mid to late 1990s. And so this again was an orbiter. It had a number of important instruments, but what I want to focus on is the well, we'll see the instrument in the next slide. No, here, the gamma ray spectrometer. The Themis camera, which we worked with a little bit in checking out that curriculum from Arizona State, is also on this mission, as was an instrument to collect radiation data, so that we would have a better idea about the radiation environment around Mars. Okay, so again, what we're really focused on here are the different components that make up the gamma ray spectroscopy mission. That's the high energy neutron detector, the neutron spectrophotometer, and the gamma ray detector. These three things together basically allow the Odyssey mission to collect information about gamma rays and other high energy particles coming off of the surface of Mars, and they can then use that data to make some inferences about what kinds of materials are present in the surface layers on Mars. So this is a little schematic about how this works. Basically, for remote sensing to take place, either the instrument that's up in orbit is collecting information that the planet is naturally giving off, which is kind of a more passive way of doing remote sensing. Or the other alternative is that the spacecraft is pinging the planet with some kind of energy and measuring what's coming back, like would be the case with a radar mission. Well, these are more passive. These are instruments on the orbiter that measure the natural radiation that's coming off of the planet. And there's a lot of details here, but I just want to make a couple of comments. First, that we're talking about relatively high energy particles. So we're talking about gamma radiation, cosmic rays that are triggering different kinds of gamma ray release on the part of elements or atoms that are in the soil surface. We have some elements like thorium that naturally occur in the soil on Mars that would spontaneously give off radioactive material. And what's really important for the water story is that when cosmic rays come in, they can collide with, bang into atoms that are in the minerals and materials in the soil. And those high energy cosmic rays, particles, will smash into the nucleus of these atoms and cause a whole lot of things to go on. And in response, those atoms can then give off high energy neutrons. So a particular cosmic ray particle could come in, smash into the nucleus of an atom, get absorbed temporarily, and then that atom becomes unstable and it gives off a high energy neutron. Or it gives off a lower energy neutron that is sort of works its way through the soil, bouncing around back and forth, colliding with different other atoms until it eventually escapes and can come up to space. Or these neutrons can go off and be captured by other atoms, the nuclei in other atoms, and lead to trigger the release of gamma ray particles, which is again different kinds of high energy radiation that the instrument can detect. Okay. So different types of elements, whether you're talking about iron or hydrogen or other kinds of atoms, they'll interact with this cosmic radiation in different ways. And so the different kinds of atoms will give off a different signature in the proportion of gamma rays and fast neutrons and other materials that are being. Okay. Now this doesn't have anything to do with water, but just to show you, this instrument is not specifically charged with mapping water on Mars. basically any atoms that interact with cosmic rays coming in can be mapped. So one of the things that they did with the gamma ray spectrometer is to just say, well, where are the heavy concentrations of iron? Okay, so by the concentrations of high energy neutrons and gamma rays that are coming off with a particular energy signature, they could indicate that, well, we've got a lot of iron concentrated in this region. So, some more here, very little iron here, which may be useful down the road if we're ever wanting to mine iron. Okay. We're more interested right now, though, in water. So one way you can look for water is to look for hydrogen in the near surface layers of the soil. So why is hydrogen a marker for water?
That's one of its building blocks.
It's one of its building blocks. So you get a bottle of hydrogen and oxygen there, right? Okay. Yeah. So this is a paper that came out relatively early in the mission, basically showing some of these results. And the take-home message is that, at least from orbit, it looks like there is a whole lot of water in the near-surface regions for large parts of Mars. And so if you're interested in water, and why are we, again, interested in water?
We need it to live.
Either Martian life or Earth life, water equals life. So basically, assuming that these hydrogen signatures that they're finding really do match up with water, in particular water ice, they're suggesting that as much as 1/3 of the weight of soil in some of these areas could be water ice. So, we would have essentially a situation where we could go out and dig a bunch of soil, bring it back into the habitat, heat it up, melt the ice out of, melt the water out of it, and harvest that water. And let's just skip this altogether. But let's look at this a little bit more. How do these neutrons and gamma rays and so forth allow them to identify concentrations of water in the soil? If you think back to that diagram where you've got a cosmic ray coming in, smashing into an atom, which then is releasing high energy neutrons and these thermal neutrons. A hydrogen atom itself is essentially a proton, perhaps a neutron, and an electron around it. Okay? So those hydrogen atoms are very well suited for soaking up and hanging on to free neutrons. So if there's a lot of water ice in a given area, those cosmic rays that are coming in may be triggering the production of a lot of neutrons, but most of them are going to get sucked up by the water, the hydrogen in the water that's in that soil, and will actually not show up as high energy neutrons and thermal neutrons that are coming up to the detector in orbit. On the other hand, when those neutrons are captured by hydrogen, what will happen is that in response to that, the hydrogen atom will give off these characteristic gamma ray signatures. So essentially, in areas where there aren't a lot of neutrons showing up in the detector, and there are a lot of these gamma rays showing up, that's an indication that that's an area where there's a lot of hydrogen. And we would then infer that if there's a lot of hydrogen in that area, then that's an area where we should be looking for water. Okay. So in this case, we have data collected at different latitudes. So here at the equator, for example, we can compare what's going on at the equator here versus what's going on at high latitudes. So the triangles and the squares are these neutrons? Are we seeing more neutrons at the equator or at toward the South Pole?
Towards the South Pole.
Over here. This is South Pole, this is the equator. These are neutrons. Do we find more neutrons being detected at the equator or toward the South Pole?
Equator.
Okay, more neutrons here, fewer neutrons here. In terms of gamma rays, if we compare the equator with the South Polar region, do we find more gamma rays at the equator or at the South Polar region? Here, okay. So at high latitudes in the southern hemisphere, we have a lot of these gamma ray neutrons. We're not seeing a lot of gamma ray particles. We're not seeing a lot of neutrons. This is basically data that says if you look in the soils in those areas, there's a lot of hydrogen. Now, why would we expect maybe less hydrogen showing up in the soils at the equator?
Less water.
Why?
Well, because it's not frozen.
Okay, why? What is it about the equator?
Warmer.
It's warmer, okay. So warmer at the equator, we would expect this subsurface ice to be baked out of the surface layers. At the equator, we would expect to have to go down much deeper to find soil that's cold enough to have ice in it. So, I mean, this makes sense. The only thing that doesn't make sense is that you don't see a corresponding, we've got a lot of hydrogen gamma rays here, then they go down. What would you expect at the North Pole?
None. Close to none or less.
Why?
Isn't it more colder?
The equator's warm, the polar regions are cold. We expect ice in the layers of the cold regions. So we're basically saying, ice here. We're saying less ice here. Wouldn't you expect ice to show up again at these higher latitudes? Somebody say yes.
Yes.
Thank you.
Yes, of course.
Of course you would. You would ideally hope to see kind of a symmetrical response around the equator for both poles. The reason why you don't see any of these high energy gamma ray particles from hydrogen is that at this time of the year, when the spacecraft was making these measurements, the North Pole is all covered up with carbon dioxide ice, which has no hydrogen in it. So that's why you don't see this here.
So it just happened to be a bad reading?
Not a bad, I mean, it's a realistic reading, but the water ice at the North Pole during this time period has a layer of carbon dioxide ice on top of it. And that carbon dioxide ice doesn't have any hydrogen in it, and so it's not going to act the same way as the water ice that's underneath. This instrument can really only detect what's going on in the topmost layers of the soil, because these gamma rays that are coming in from space don't penetrate very deep into the soil. That's why if we build underground habitats, that would be one way to help protect us from radiation. But in this case, because there's carbon dioxide ice on top of the water ice is essentially hidden to this process because it's too deep. So here's the kind of map that they come up with for neutron counts. Okay, so again, low levels of neutrons, like you see down here and like you see up here and around in here, means more hydrogen, which they're inferring means more water. And in areas that you would expect to be warmer and drier, like the whole Tharsis area here, you see a lot of these neutrons because there's not a lot of hydrogen to soak them up. And so this was kind of important results when it came out because it indicated to the not only scientific community but people who are just interested in Mars in general that there's likely to be, assuming we're interpreting these results correctly, there's likely to be a lot of water available to us when we go to Mars if we just dig down in the soil and get the water ice out of it. That's remote sensing though. We've got a spacecraft up in orbit and it is collecting this information off of the planet and we have to interpret what it means. It's very important for remote sensing data to be validated by someone on the ground who's actually taking real measurements. And currently we don't have any someones on the ground on Mars. But what we do have are robots, so Mars is currently a robot planet. And the Phoenix lander mission was sent to some of these high latitude areas, just a little bit below the North Polar Cap, to dig around in the soil and to really validate that information that we'd been seeing from orbit. Again, we've got in this case, a stationary lander sitting on a northern plains vista, and it's got this scoop that can reach out and dig into the soil. And this just shows all of the different areas down here where they were, collecting samples that are within reach of the arm on this robot, not rover. Okay. The take-home message is, yes, they found ice, and they found that ice was water ice, so they basically confirmed the results that we got from the Mars Odyssey instrument looking from orbit. It was an interesting mission. It was a short mission because it landed and could only work until the North Polar winter basically killed off the spacecraft. There was evidence seen quite early that there was a shallow ice table. Let me blow this up a bit. For example, it's not going to show up unless I kill all the lights. Well, you can take a look at this later. There are little bits of ice that were exposed by scooping out that bit of soil. And what happened, they then just visually monitored them over time. If those were carbon dioxide ice, they would have sublimated right away. But over the course of like 4 days, once that ice was exposed, it evaporated into the atmosphere. So that's consistent with the Odyssey results. You can kind of see the layers of subsurface ice that are exposed in these different scoops. Now, this is just a map of where they found icy soil, where they found soil samples that didn't contain ice. The take-home message is that they found a lot of ice in the soils around, but not totally. They also appeared to have uncovered a whole shelf of ice when the lander landed. So this thing came down not on airbags bouncing around. This came down on retro rockets. And so the retro rockets at the very last, when it's actually just setting down, it's going to blast away all of the surface layers of the soil. And when they looked with the camera underneath the lander, they saw what they interpreted to be just basically a layer of fairly pure ice that had been covered over by some soil, and that soil was all blasted away by the rockets as the lander came down. Somewhat interesting and controversial, there was some evidence that water droplets were basically developing on the struts of the lander, or accumulating on the struts of the lander over time. Something was drawing, water out of the atmosphere and having it collect on the different parts of the spacecraft. And probably what was going on is that this ice here is very loaded with salts, so that it's a very salty brine. And those, some of that salty brine got blown up by the retro rockets when melted and blown up by the retro rockets when the probe was landing. Those droplets of brine fell on the spacecraft and became kind of all that salt in that frozen brine became kind of a magnet to attract other water out of the atmosphere and accumulate in that way. We won't go into the actual results in a lot of detail. They essentially had a chemistry lab, which is what this is. So the ability to take soil samples and ice samples and dissolve them in water and measure how much salt is in the sample, of what kinds, how much, what conductivity and so forth. So this is essentially a chemistry kit. And over here they had a set of ovens where they could bake soil samples and see what kinds of materials came off. And just some of the basic results is that clearly they did find water ice. They could confirm that what they were looking at visually was indeed water ice, that the subsurface layers of the soil were just full of this water ice. It's moderately alkaline. So the sound bite that the press picked up at the time was, "Oh, this is water you'd like to grow asparagus in." Why asparagus was the sound bite, I don't know. But the mineral composition of the soil, the alkalinity and pH of the water and so forth indicated that by and large this might not be such a bad environment for getting resources for growing crops when we do go there. Evidence for carbonates, which again we would have expected to see all along with the carbon dioxide and water history of the planet. And what's important for down the road when we're talking about the Viking experiments is that they found evidence for this class of compounds called perchlorates. So perchlorates are basically an oxidizer. It's a compound that can readily oxidize other materials. If you look at the shuttle solid rocket boosters, they include perchlorate as part of the oxidizer for the solid fuel mass that's in the solid rocket boosters. Perchlorates on the Earth are oftentimes a pollution thing that we have to clean up after dry cleaning places or in various industrial situations. But the fact that we've got perchlorates naturally occurring in the soils on Mars has some indications, again, for the Viking results that we'll talk about later today. And there are some microbes on Earth that actually use perchlorate as a food source. So that was kind of interesting as well when it was announced. Okay, so take-home message of that part is that through remote sensing and through the ground truth that we got from the Phoenix mission, there are large swaths of Mars, middle to high latitude areas, where there is a significant amount of water ice just bound up in the surface layers of the soil. And so that would be a ready reserve for us. The other main reservoir for ice, besides the polar caps and the subsurface ice, would be glacial formations. And I don't want to spend a lot of time talking about this because we've already talked a little bit about glaciers earlier in the term. But, you know, with glaciers, we're talking about snowfall accumulations that get converted into these ice flows. The glaciers can be very important in terms of sculpturing the landscape. You know, glaciers moving across the landscape can carve out channels and other structures. And so, you know, those glacial, if we can find glacial structures on Mars, those clearly would be large current sources of frozen water as well. Pretty glacier pictures, okay, so. Where do we find glaciers on the Earth? North and South Pole. But where else do we find glaciers? We find glaciers actually on the equator. But where on the equator? No, on top of mountains. So Mount Kilimanjaro, I only saw it from a distance from the Kenya side of the border. It's actually in what do we call it now? Tanganyika. But you know, it's pretty much almost on the equator, and it's capped with glaciers at the top. Clearly in the Alps, you know, other in the Himalayas. Basically, where it's cold enough for snow to accumulate, more snow to accumulate during the snowy season, that then gets melted off during the warmer season. So if you have an excess of accumulation of snow in an area, that snowpack will build up, and the pressure eventually converts that snowpack into an ice flow, and that ice flow can move across the countryside in response to gravity. I mean, glaciers, generally speaking, flow downhill, and they carry lots of rock and other debris along with them as they move. We have other things besides straight out ice glaciers, though, and these might actually be more important for Mars. We have what are known as rock glaciers, which essentially just have a much higher proportion of rocky material to ice. I mean, you've got a continuum. You could have almost a fully rocky slope, but if that rocky debris slope has enough ice in it, that ice will tend to lubricate the flow of the rocky material, and that rocky icy mixture itself can flow downhill just like a more traditional icy glacier. And you have essentially everything in between, depending on, you know, what is the balance between water ice and rocky material in these flowing features. But in any regards, I mean, whether it's a rock glacier or a icy pile of rocks, or a ice glacier, or a somewhat dirty, contaminated, rocky ice glacier, anything in between, we recognize those, generally speaking, by how those features basically flow down hillsides in response to gravity, and the effects they have on the landscape as they do so. Let's skip that. So we've already seen some figures, structures on Mars that clearly look like they are flowing features, either glaciers or rock glaciers or something in between. Here's just a classic example in the Hellas Basin area, where we have a higher elevation small crater and a lower elevation larger crater with a break in between the two, and it clearly looks like snowpack has been accumulating in this upper crater area forming an ice flow, and then that ice flow has been flowing down to fill in this lower crater. Classic kind of linear flow that we would expect from a glacial feature. Here's just another example of these lobate flow features on the side of Olympus Mons, and how that would compare to a similar structure here on the Earth. The one on the Earth is from one of the Antarctic dry valleys. Okay. Won't go into any detail here, just that in general, many of these features that look like they are glacial or rock glacier structures tend to look very young. They don't have a lot of cratering that's accumulated on top of them, which is what we would use as an indication that they're relatively young features. So many times we're talking about features that are some few tens of millions of years old, or even younger than that. We see some of these glacial features where you don't find any craters at all, and so you can't really establish what the what the age is, because it hasn't accumulated any glacial impacts or any crater impacts yet. Just again some of these morphologies. You can kind of see these what look like flow patterns showing up in how these masses have moved down the hill. These are images from a location on Mars. Here's a glacial flow in Canada showing the same kind of what they call lineated valley fill. So these structures that fill up the valleys and appear to be flowing down the valleys based on the kind of linear features that show up in them. Lots of just Mars versus Earth and Mars versus Earth comparisons. Again, the way, this just highlights our use of analogy that we've talked about before. Trying to understand what's going on in what we see in these images from Mars based on images of structures we can actually examine and explore here on the Earth. Okay. So why are these interesting, and how do they relate to climate? Many of these glaciers are showing up at latitudes where we know clearly that there is not snow accumulating at these times. Okay? These Pavonis Mons, for example, is right on the equator of Mars. And clearly there is no snowfall on the equator of Mars today. These other Tharsis volcanoes, Olympus Mons, these are not areas where you would expect snowpack to accumulate. So how do we explain the fact that it looks like there are glaciers there? What? Well, elevation is clearly important, but even and these, Mount Olympus is taller than any other volcano on Mars. These Tharsis volcanoes are also relatively tall, but even as tall as they are today, there is not any. I can guarantee you, there is not any snowfall happening on Olympus Mons today. Okay, so if there's no chance for snowfall to accumulate today to produce glaciers, our only explanation is, well, perhaps at some point in the past, the situation was different, and there actually was snowfall on Mount Olympus, and enough snowfall to accumulate over time and to create this snowpack that turns into this ice flow, glacier sticking on the side of Olympus Mons. And somehow it has managed to hang out until today. And that hanging out is probably the result of the fact that these glacial features on Mars rapidly get covered over by rocks and other debris as surface layers of ice melt away. And so that provides an insulation that can keep the ice around for apparently tens of millions of years. So this ice is probably are at least tens of millions of years old and accumulated there at that time, and we're seeing the residual glaciers today.
We should just dump tons of like gravel on all our glaciers so they don't melt due to global
Yeah, so that we don't lose our glaciers. Yeah, there might be easier solutions,
Yeah.
like actually dealing with the problem.
Yeah, exactly.
What appears to be going on Mars, and this is just probably looks like something that makes no sense to you, but as we talked about before, Mars wobbles back and forth on its axis much more than the Earth does. The Earth has been pretty much 23-degree tilt for millennia. Mars currently is about 25 degrees, so it looks like it's acting like the Earth. But we know from a variety of orbital mechanics models and other things we see about Mars that Mars is much more like a wobbly top than the Earth is. And so currently it's at 25 degrees tilt, but there are other times when it is 15 degrees, so it's much more upright, much less tilted than the Earth. There are other times when Mars is tilting over as much as 35, or sometimes this only goes back a few million years. There are good models to suggest that Mars can be as much tipped over as 45 degrees on its axis, which is quite a different situation than what the Earth has, and quite a different situation than what Mars is doing today. And just the take-home message for that is that as Mars wobbles back and forth on its axis, where snow and ice accumulates varies. So when Mars is much more tipped over, the polar regions get a lot more direct sunlight at different times of the year, and so water, ice, and carbon dioxide get melted off of the polar regions. And where that water ice accumulates tends to be in a much more equatorial location. On the other hand, when Mars wobbles back the other way and is even less tipped over than it is now, that ice that had accumulated, say, on the side of Olympus Mons or those other volcanoes, eventually distributes itself back out back to the poles. So we're looking at Mars right now in its current situation, but the take-home message here is that Mars is much more variable in its climate than the Earth. It doesn't have many of the same stabilizing mechanisms that we have, and so really to understand what's going on with the ice on Mars, you have to take this into account, because we cannot explain why those glaciers are where they're at today based on Mars's climate today. And when we actually get to Mars and can take some real samples from some of the terrains on Mars where these climate cycles may be represented, then we'll be able to nail this down in better detail.